it's a collection of different types of graphs, and it comes from section 2.1 and 2.2. And there are lots of different ones. We really build only the stem leaf plot from scratch on paper. Some of the other ones are actually using Sophia, and we'll do that. We have a stem leaf plot. The line graphs, time graphs, and frequency polygons are actually very similar, but they have very specific characteristics and rules that we're going to look at. And then we have a few other graphs where we're just kind of learning what they're called and not necessarily interpreting as much. So stem leaf plot, that it has such an odd name because in a way you're building almost like a tree, and you have a stem and you have the leaves that come out of that stem. So here is the data that we're going to use as an example. We have the data set list, the number of text messages sent in one day by 50 cell phone users. Display the data in a stem leaf plot and describe any patterns. So that's a lot of data, but for the stem leaf plot, it will make a lot more sense to actually put them in order. Now, you can always put them in order yourself by hand. I like sorting them in the calculator, especially if you use data for more than one type of problem. And I know it's tedious, but that's what we're going to do. I'm all about using the calculator because it's a tool that you all can have. You can check out a TI-84 calculator from our library for free. The only time that you ever pay for it is if you return it in bad condition at the end or you don't return it. Okay, so make sure if you haven't done that already, make sure you check that out. This might look scary from my calculus class. We don't really use that kind of graphing. So I'm going to go to the stat key like we did before, and we're going to enter the data in edit. So I'm going to press 1 or enter. And I don't think this is the data for this problem, is for something else. So I'm going to clear this list. So you move your cursor to L1, clear, and enter. And now I'm going to start entering them. And you should do the same. Like I said, it's a little bit tedious. I'm going to actually enter the columns because it's easier for me to keep track of it. So I'm going to start with the first column, 76, press enter, 122. You press enter after every entry, 66, 76, 41, 26, 33, 29, 23, 38. And that looks like it's 10 entries in each column. And that gives me a chance to double check and make sure that I've entered everything correctly. Even though it takes time, it pays off when you actually do the sorting. It really helps you out. So now I'm going to go and enter the second column in the same list. So I'm just going to continue there, 49, 76, 80, 115. And if you make a mistake, if you catch it right away, don't be afraid, just move up and override it. So it should be 80, enter, 115, enter, 86, 29, 24, 32, 33, 34. So that's the next 10, should be the 20th entry. Now I'm going to go to the third column. So I have 102, 89, 78, 99, 48, 33, 43. I do this by hand when there are fewer than this. but keeping track of those is kind of hard. So that's why I like to do it on the calculator. Then we have 30. And 33, 53. Now the next one, 58, 67, 69, 72, 52, 26, 16, 29, 41, that's you, 30. One more. So that was the 40th entry. So now one more column, 88, 80, 56, 19, 28, 20, 39, 40, 33, and 149. So what I want to do is I want to order them from the smallest to the largest. That becomes helpful when you're constructing your frequency distributions and histograms. It becomes really helpful when you're doing the stem leaf plot. So now you go back to stat and you sort, and I'm going from the smallest to the largest, so that should be number 2, sort A. You have to tell the calculator that it's in this one. So that will be, notice that the lists are in 1 through 6 in the keys. That says 1 through 6 in blue. So you go second and 1, and then close the parentheses. Press enter, and it says it's done. But if you go back to stat and edit, now you see them in order. Again, you could do this by hand, but think about it. You're going to have to order 50 entries, and sometimes you may miss one, and you may have to actually rewrite it and erase it. So I'd rather do it on the calculator when there are so many. It pays off. Okay, so let's come back to the handout. And one of the rules for stem leaf plots is that you have to be given the key of how the stem leaf plot needs to be built, or you have to decide what the key is. So the key will look like this. The key would be 2, and then they have a line through it, and 5. So that means this is called the stem, and this is called the leaf. It is equal to just an entry of 25. So it looks like we're using one digit, the first digit as the stem, but then the second digit as the leaf. But what happens if you have something like 149, which, by the way, I think is your highest entry? So you're going from a stem of 1 to a stem of 14. This would really be 14 space and 9. This is the stem, and this is the leaf. So just because the key, let me highlight the key, just because the key is 2 and 5, that 2 actually will go from 1 all the way to 14. Okay? So that means that I'm going to go to the next page. In here, I'm going to have, again, the stems. In fact, I should have written stem here. And here are the leaves. I'm going to have to make it smaller. And so now in the stems, I'm gonna have to fit the numbers 1 through 14. And if you look on your calculator, the smallest entry is 16, so that's why I'm starting with 1. And if you go up, it takes you to the bottom, and your largest entry is 149. So your largest leaf is 14, is 149, so it's 14. So in here, I'm gonna have to write 1 through 14. So now in the part where it says the leaves, you write that second digit that is actually the leaves. And that's why it's helpful that it's already in order. I'm gonna go to the top. So I'm gonna go down this way. So how many numbers do you have with a leaf of 1? 2, right? 16 and 19. So you're gonna have here, you're gonna write here a 6 for 16. We don't put commas in here, and leave enough space for the 9 for the 19. And that's why it was helpful that they were sorted already for us. So how many leaves start with a 2? Well, I'm gonna have to go down a little bit further, because so far I see 5, 9, but they may be more here. So they're actually 10. And some of them repeat, but I have to actually use that many leaves for each of the numbers. So I have only 120. I have only 123, so I put a 3. I have only 124, but I have 2 26s, so I'm going to put the 6 twice. I have a 28, and then I have 4 29s. So then I'm going to put 4 9s. Now I have to do the same thing for the 30s. And I'm going to scroll down. Right there. Did I miss one at the very top? I think it started with 30. Yes, no, I think I did. Good. So again, I have 10 entries that start with a 3. But if they repeat, I still count the leaf as many times as they repeat. So I have 2 30s. So then I would have 0 and 0 for each of those. I have 132. I have 4 33s. I have a 34, a 38, and a 39. And we keep doing that until we count all of them. But this is why I ordered them. I don't, on the calculator, I sorted them. Not because it's impossible to not do it by hand, but it's because I may miss something when I'm actually ordering them like that. But it's not impossible. So now I have actually for 40, I have actually 6 entries that have a 4. And it's 40, 2 41s, 143, 148, 149. So now I'm gonna look at the 50s, and I have 4 that have 50s, starting with 52. 53, 56, 58. Any questions about what we're doing? Okay, so now the 60s. They're fewer. They seem to be fewer now. So then I have 360s. So I have 66, 67, and 69. For the 70s, I have 72 through 78, so that's 5 of them. So I have 72, 3 76s, so I have 6s and a 78. I'm going to scroll down because I don't know that I have all the 80s in there. Okay, so it looks like I have 5 80s. So I have 2 80s, so I put 2 zeros, 186, 188, and 189. And then I just have one of each after that. I have a 99, 102, 111, 122. And notice I don't have a one that starts with 13, but in my leaves, I actually still leave a gap in there. So I have a 99, 102, 115, and 122. Then a gap for 13, not a zero, because a zero would mean you're saying you have 130. But nothing here means you don't have any numbers that start with 13. And then we have 149. I'm gonna write a note here, and sometimes I like you to write the note is leave a space if no values in that stem. Sometimes when you're looking back at your notes, if you don't write yourself notes like that, you might think, oh, I made a mistake, or there was a number, or I should admit it. But this way you know that you actually have to leave the space, or any other place that you have them in there. Now, if you look back at the problem, it says, describe any patterns. So once in a while when we get here and I say stem leaf plot looks a lot like a histogram, people look at me and think, what is she thinking? You know, the histogram has bars. So I want you to do something. I want you to turn your face to the right and look at the patterns that you have created here. When you look at that sideways and you think about this being bars like the histograms, where is the highest frequency? What class or what stem? Stems 2 and 3. Which one has the least frequency? 13, because it has 0. And then where are some of the data clustered together when you look at it sideways like that? Where are the most of those entries? I would say in the first, the first 8, that's where it had the most, and then the least would be here. So there are a lot of things that you can say about that when you think about your leaves is telling you how many entries you have. In a way, like frequency. They're not classes, they're stems. And they're not bars, but they're lining up and you're seeing you have that many entries in there. Any questions on that? So that's one, the histogram that comes from the frequency distribution we build from scratch. You'll be expected to build from scratch on your test. A lot of times in Sophia they're multiple choice because it's easier electronically. But if I build something from scratch, then it's because I expect you to do that. Stem leaf plot is another one where you'll be expected to build from scratch on your test. So that's why we're taking the time to do that. But a lot of other types of graphs we're just learning what they are and how they work because we are interested in interpreting some of the information that we're given. So we start with line graphs. These are pictures from your book, you know, the OpenStax ebook that you have. I cannot say a specific page because you have it in electronic form. The only way that you can refer to a page is if you print it, but it actually comes from section 2.1. And it says, in a survey, 40 parents were asked how many times per week a teenager must be reminded to do their chores. And the results are given here. This is the number of times a teenager needs to be reminded of their chores. And this is how many parents actually said they have to remind their teenage children to do their chores. So now, when you graph that, so it's still a frequency, it's not a class per se, this is not a class, and the number of times a teenager is reminded will still be on the x-axis, but it's not a class like we did with histograms. It's just the number of times you have to remind a teenager to do their chores. Then on the vertical axis, still the frequency. And if you notice, 0 times 0 reminders, the frequency is 2. Notice this is 0 for the reminders and the frequency is 2. It's a point, but then they're connected. So every one of those points corresponds to the frequency for each of those categories of the number of times, but then they're connected by line graphs, by line segments. This is what a typical line graph looks like. Now, there are a lot of other versions of line graphs that have very specific characteristics and instructions. We have time series, we have frequency polygons. All of those are also, in a way, kind of line graphs like this, but they have very specific rules. But this will be a typical line graph or straight line graph that we have here. Now, the next one is a time series graph. So before we actually look at Sophia, oh, and I had written in myself a note here to tell you. So on a typical line graph, let's come back over here. Because you're gonna start getting them confused. So a typical line graph starts on the first X value with its frequency. In a way, and I'm gonna put F here, frequency F. In a way, like you do in algebra, and what I'm saying, it seems like a minor thing, but things are gonna start changing in the next ones. So what I want you to realize, what I'm saying is, these are your X's, and this is F in here. So this is saying that this point starts with the first X value, which is 0 reminders, and its frequency, which is 2 from the table. Again, seems like a normal situation, but in the next couple of examples, things are going to change. So I wanted to make sure you wrote yourself a note here. Now, we're going to do this one. I actually did a video this morning. I was hoping that, you know, I say I'm a morning person, but really I'm a morning person that thinks better after my first cup of coffee. So I made a video to do this question for, because it's very tricky, but it didn't actually work exactly as I intended it. But I do want to show you the video. And what I say and I do there is what I would normally do anyway. So one of the first things before we do anything else is time series graphs are a lot like line graphs. But what differentiates them is that your X values represent time or time periods. What I mean by that, they may say sometimes the year 1999, or they may say from 1999 to the year 2000, or from the year 2000 to 2001. So that's what really makes everything very different in this time series. So we're going to look at question number 4, and this is actually on assignment 6. That's what this section is. Just take notes or watch this carefully. It's really just like if I would open Sophia and do it from scratch. Okay, I'm going to stop it. So when you're looking at the year, you see it on the x-axis right there. And when you're looking at the number, which is a little bit like the frequency per se, you see it on the vertical axis. And the actual points are exactly on the intersection of the year and the number. So that seems very similar to what we just did. And so, for example, 1992 here will be at 110. 1994 will be at 109. 1996 will be at 106, and so on. But you're adjusting, you're taking that little line graph in Sophia to put it there. And it doesn't seem that difficult. We're going to finish it up. And I don't see a mistake with that. I don't see any problem whatsoever. But you're gonna see me check the answer and it's gonna say it's wrong. It's very sensitive. Like I see something a little bit odd in here. So I know this is a little bit off, but or maybe even this one here, but I tried to fix it several times and I couldn't. I don't want you to get frustrated with that. Now, take your time and make sure you're doing it correctly. And if you do it twice or you do it again and you're certain that that's correct, I want you to send me an email and again, tell me you're on assignment 6, problem number 4, and I can check it manually. But I know I'm a little bit off in here. See how the dots seem to be a little bit bigger? It's that finicky, but I couldn't fix it. I tried it. This is not the first video I made this morning.
The last thought.
Take
The last thought.
the last dot?
The very last one.
Maybe that's why. Okay. So see, don't give up because that's exactly what they're saying. I put that in 103. That's completely wrong. And it should have been in 102. But I promise you, I tried it before and I probably didn't make that mistake. But it's that finicky. Okay? So just don't spend an hour trying to get this right because you want 100 on that homework assignment. But be certain that you are at least in the right place. And then send me an email and I will check your assignment manually. I can actually see what you have done in a particular homework assignment, but tell me the question number and the homework problem, okay? But this is what a time series looks like. And if you notice, it's not just each of the X's represents a time, like in this case, a year, but the line segment represents like an interval from 1992 to 1994, from 1994 to 1996, and so on. So that's what differentiates this from a time series. Actually, let me minimize that. And let's go back to our notes. So you may want to even write yourself a note there. Watch out for your points. Email Mrs. Bauer if wrong when you're doing that problem number 4. All of these ones are technically line graphs because we're using the XY plane, but they all have very different mechanics, different characteristics. For example, a frequency polygon. Bless you. It looks like what you normally have as a frequency distribution, and this looks like the lower bound and the upper bound. It doesn't say that, but of class boundaries. How do I know that they're not class limits? They're actually class boundaries. Because they're touching. You see, they're overlapping. 59.5 and 59.5. Class limits do not touch. They do not have anything in common. So this, even though you may not need it for this example, but this right here, these are class boundaries. And it's given to you. But they may not specify that. So these are the class boundaries for a frequency distribution. They give you the frequency F, and they give you the cumulative frequency. I'm going to call it CF, but there's really no formula. Remember, that comes from the first one is 5, then you add a 5 to the 10, and it gives you the 15. You add 15 to 30, and you get the 45, and so on. That's how you get the cumulative frequency. But this was given to you, okay? We don't have to necessarily work it out in there. But a frequency polygon relies on the midpoints. So I'm going to need to calculate the midpoints here. So I'm going to start out with the first class, and I'm going to calculate the midpoint. And that is 49.5. That's the lower bound or lower limit, plus the upper bound or upper limit of 59.5 divided by 2. So that gives me exactly 109 divided by 2 is 54.5. And now here, I'm going to start putting the midpoint. So then this will be 54.5. Now, I could calculate the midpoint for every class, but I could also use the class width. And remember, the class width is not, a lot of times we think it's the difference between those two, but it's not necessarily the case. Sometimes they are the same, but it's actually the difference between a lower bound of one class and the lower bound for the other class. So how many units is that from 49.5 to 59.5? 10, right? So then that means the class width is 10. It's just coincidence that is also the difference from the lower bound to the upper bound. That is only coincidence. Class width is the difference from one lower bound to a next lower bound, or from an upper bound to an upper bound. But it's also the difference here. Like if I add 10 here, then I'm going to get 64.5. Add 10, and I get 74.5. Add 10, and I get 84.5. Add 10, and I get 94.5. And that's a lot quicker to find the midpoints than it is to actually use the midpoint formula. Questions so far there? So now with this, we're gonna build a frequency polygon, and that's actually very different. You have the graph on the next page, but there are a couple of things that are a bit odd when you look at that graph. I see the midpoints here. I see the midpoints that I found: 54.5, 64.5, 74.5, 84.5, 94.5. I see those, but I see extra. So one thing that is very different with the frequency polygon is that it doesn't start on the first midpoint. Starts before that. So this is before the midpoint of the first class. I don't like the way I wrote that. And notice, it doesn't end with my last midpoint. It ends with that 104, and that is after the midpoint of the last class. But how do you know what that number is going to be? We still use the class width. You're really taking 54.5, which was the midpoint from the last class, minus 10, and that gives you 44.5 to find the first point. And here you're taking 104.5 and you're adding the class width. Oh, I think I may mess it up. It should be the 94.5, the midpoint of the last class that we calculated, plus 10, and that gives you 104.5. You're given this. You're not going to have to construct it, but there are some, quite different, some definite differences from a regular line graph. A line graph will start with the X and the frequency. Here, those are midpoints, and it starts before and it starts after. Now, when you look at the Y, that still represents the frequency. And that's what we call a frequency polygon. So we have straight line graphs that start with whatever we designate X to be and the frequency. That's where the points are, and you join the lines. We have the one in the video, which is the time series graphs that each tick mark on the x-axis represents a time, but the line segments represent a time interval. And so those were different, but that started really with the first year and the first frequency, kind of like a line graph, except that the x-axis were time series, there were time intervals. And then the one that we're looking at right now, the frequency polygon is very different because it doesn't start with the information that we had. It actually uses the midpoints, and it doesn't start with the midpoint. It actually starts on the x-axis. In other words, that beginning and that end don't have a frequency. Notice they start at 0. This is where you start measuring your frequency at the midpoint of that particular class. So that's actually different from the other two, but still very similar because we're actually doing line segments and using the frequency for the y-axis. Okay, the next two, we're not constructing them, but I want you to know what they are. So what you have learned maybe in other courses and in the past is bar graphs. What you see in a lot of presentations that talk about like opinion surveys, they're usually bar graphs. This is not a histogram. Notice that on the x-axis, I don't have numerical values. I have quantitative data, like the favorite type of movie. Now, I do have a frequency on the y-axis. How many people said their favorite movies are romance or drama or sci-fi? Okay, so, but they're not histograms because I'm not forming classes. And notice that they're not touching each other. Remember, we made a big deal about the histograms. We use the class boundary so that they touch each other. So that's called a bar graph. It's really not a histogram. And a Pareto graph is a bar graph, but they're actually in descending order from the smallest. Actually, sorry, the other one. From highest to lowest. That's what differentiates a regular bar graph from a Pareto graph. And it makes sense why they would want to use the Pareto, because I can tell right there, I can ask you, what are the 2 top leading causes of death in the United States? You can see because they're the tallest, heart disease and cancer. And of the 5 top causes of death in the United States, which one is the lowest, but still a top 5? Strokes. So there's a reason why you would want to put them in order, and that will be a Pareto graph. Now, the next one is called an ogive, and we're going to look at it in Sophia, but we need to do a little bit of work. And when I open problem 9 on assignment 6 on Sophia, it's going to change our numbers completely, okay? But I want you to work with this by hand because a lot of times you have to calculate this. So by the way, an ogive is a line graph for cumulative frequency. So technically, you're given the frequency here, but you should find the cumulative frequency. And what happens a lot of times is in your homework, you have to fill in those blanks to find the cumulative frequency. So remember, the cumulative frequency for the first class, I'm going to make this a little bit bigger, is a 3. But after that, you're adding that 3 to the frequency from the previous one, and you get 13. I'm not going to draw those lines, but you're adding the 13 to the 11. I don't want to keep putting the lines because it gets confusing. But then 13 plus 11 will give you 24. 24, maybe I should add the lines because I'm getting confused. 24 and 11 will give you 35. 35 and 14 will give me 49. 49 and 3 will give me 52. 52 and 1 will give me 53. I was hesitating because I think my numbers are actually different, but it's because it would change what the problem is when we do it. Okay, so now when you do that, remember, if these are all your cumulative frequency, so I want you to write this note, even though right now we haven't even looked at what the ogive looks like. So on the start line, the mark or start line is on the upper class boundary of a class. In other words, this one's here. I told you every graph has its own rules and distinctive differences, and that's what's going to happen in here. But we are going to look at problem number 9, and we're going to do it live. But I want to warn you, when I do that, it's going to change what these numbers are. But I wanted you to have this on your paper, so you write yourself a note and you remember what the cumulative frequency is. So I'm going to go to, I didn't make a video for this one. So we're going to go to Sophia, assignment number 6. Problem 9. The order will always be the same, but the problem may be different. You can compare it. It's actually different from the one you have on paper. Okay, so it doesn't ask you to calculate the cumulative frequency. It's actually multiple choice. So you will have to check what the cumulative frequency is because these numbers here are not the frequency. Okay, so let's do the first one. Okay, so remember what I said, that you actually you use the upper class boundaries. So that means that the first little line should start with 99.5. That doesn't look like it's 99.5, so I couldn't use A. That one doesn't work. But that was actually my lower limit. So it should be, it should be 104.5, the upper boundary. So, okay, coming back. So this one is not starting with 104.5, but then C and D are starting with the upper boundary. So I know it would be C or D, okay? Only by looking at the fact that, or thinking about the fact that the starting points or any of the points are using the upper class boundaries, okay? That's how I decided C or D. But then it didn't ask me to calculate the cumulative frequencies, but I have to. Now, the first class will have a cumulative frequency of 2. So that could be a deciding factor, but I think they're both starting with 2. You see that? So it doesn't help me. What will be the cumulative frequency for the next class? Remember, it's 2 here. What would this one be? What? 13. So now I'm going to check here. And so they both look to me like they're on 13. So now, if this is 13, what will the next one be? 26. So I'm going to check that, C and D. So they both look, no. I see a difference now because this one is really close to 30. This one is really close to 25. So I think that I can already decide here that this will be C. That's correct. You see that? But you have to sometimes calculate your cumulative frequencies to see where they start doing different, putting different numbers, and only one will be correct. Any questions about this jive? So some of your exercises is where you're given the graph, the type of graph, and you have to decide which one is the correct choice. But you have to know some of the rules. And the rule here is that an ogive is, that's why I asked you to write this in here, even though I knew it's going to change, that an ogive is a line graph for cumulative frequency. So you would be better off on paper finding your cumulative frequencies, because that's going to be your points. That's going to be your Y values on the vertical axis. But then you use the upper class boundaries as your X's where you're starting. And that's how I eliminated choice A and B right away. Questions? Okay, so this is the end of assignment number 6. So that means assignment number 6 is due next Tuesday. I have a new handout and we'll start talking about 2.3. So if you want to come and grab one, we may not get super far, but we'll start it. So assignment number 6 is due on Tuesday, February. Trying to think. 6, 4, think 3rd. Yeah. So in section 2.3, we continue representing data, and one of the first representations is actually called a percentile graph. And so there are certain rules. So the percentile graph, I would say here, 1 through 3, kind of relate to the same type of graph, but different situation. And then parts 4 and 5 relate to a frequency distribution, but different aspects of it. And then number 6 is actually very different from the rest, because we use what is called quartiles. So they're almost like they're all like different concepts, but they're all kind of related and they're grouped together here in section 2.3. So we're going to start with the percentile graph. So the first rule is that the first point is on the lower limit of the first class boundary. That helps. It's not like that other one that starts with like 10, the class width to the left, the class width to the right. It kind of helps that it starts actually, but it's on the lower limit of the first class boundary. Then it is a line graph because we're going to have little line segments, and the points lie on the upper limits of the class boundaries. So I should say the rest of the points. Will actually be on the upper limit of the class boundaries. The other thing that makes it a percentile graph makes it very specific is that it uses cumulative percent. We have not studied this, but we have noticed cumulative relates to the cumulative frequency. So it's actually the cumulative frequency divided by the total number of data entries. So I'm going to say CF divided by N. And that gives you a cumulative percent. Now, the horizontal axis contains the class boundaries. That seems, kind of like a histogram where we actually use the class boundaries. And then the vertical axis contains the cumulative percentages of each class. So I'm going to write this over here again so you realize the cumulative percent is the one that is equal to the cumulative frequency for a particular class divided by N. So this percentile graph is really a graph about the cumulative percent. And I just reiterate the same thing.